Right, let's do the arithmetic circuits test question from Thursday of this week, which was revolving around computing 3n plus 2 for a 2-bit number. Part A of the question asks us for the truth table for a full adder. So we're adding 3 1-bit quantities, let's call them x, y, and z, and getting out a 2-bit number. As ever, we tabulate all possible inputs by counting to 7 in binary. And now we compute the outputs just by adding up the 3 inputs and giving the answer as a binary number. 0 plus 0 plus 0 is 0. 0 plus 0 plus 1 is 1. And similarly, 0 plus 1 plus 0 is 1. 0 plus 1 plus 1 is 2. 1 plus 0 plus 0 is 1. 1 plus 0 plus 1 is 2. 1 plus 1 plus 0 is 2. And 1 and 1 and 1 is 3. So we have the truth table for a full adder. And next we're asked to make a full adder using only AND gates and XOR gates. But we are allowed to make useful intermediate components. And a very sensible useful intermediate component to choose is to make a half adder that adds only 2 bits. And you can see the truth table for a half adder is hiding inside the truth table for a full adder. It's how to add 0 to 2 more bits. And if we look at the outputs, we see that the 2's is given by and the 1's is given by exclusive OR. So we can make a half adder to add 2 bits from AND from XOR, just feeding the same inputs to both. And now, to build a full adder from half adders, we add the bits 2 at a time. So we have 3 inputs of place value 1. We add the leftmost 2 with a half adder, and out come bits of place value 1 and 2. And then we need to add a bit more, add the other one in with another half adder. Out come the 1's of the answer, but we also have another signal of place value 2. Then to produce the 2's overall, we only need the 1's column from adding these 2 signals of place value 2, so we can do that with an XOR. It's the XOR that comes from the 1's column of the half adder that has place value 2, and we're done. We've made a full adder from 2 half adders and an XOR gate, ultimately everything from AND and XOR. You can tell that we don't need more because the largest 1 and 1 and 1 can get is 3, so we are not going to need a 4's column. Okay, moving on, we are asked to take a 2-bit binary number. Let me just give myself a little bit more space. A 2-bit binary number, so place values 1 and 2. And if we call this number n, we're supposed to compute 3n plus 2. And we are told, and if we think about it, the biggest this number could be is 3. And what's 3 times 3 plus 2? It's 11. That would take 4 bits. So we're going to need to give out a 4-bit number with place values 1, 2, 4, and 8. And we're told that we have access to 2 full adders, but also constant signals of 0 and 1. We're also given the hint that that to double a number, it's sufficient to move all of its bits one place to the left. So in particular, we know that 3n plus 2 can be given as 2n plus n plus 2. Okay, so how do we move the bits of a number one place to the left? Well, we make a copy of each bit and assign it the next place value up. So this copy of our 1's column we assign place value 2, and this copy of our 2's column we give place value 4. And now we need to add an extra 2. One way to do that is simply to introduce a constant 1 signal also at place value 2. And now we have all of the things that we need to add up. So we just need to remember the recipe for adding, which is to start at the lowest place value and ask, how many signals of it do we have? And we have just one signal at place value 1, so no adding is necessary. This is already the output. And if you think about it, what this is telling us, the 1's of the input is telling us if the input is odd. And if n is odd, 3n plus 2 is also odd, because odd times odd is odd, even times even is even. So 3n will be odd, and 3n plus 2 will also be odd, exactly if n is odd. So the 1's of the answer is the same as the 1's of the input. Okay, so we finished with place value 1. How about place value 2? Well, we have 3 signals of place value 2. And we also have a full adder. So we can add all 3 signals in one go with the full adder. And what comes out will have place value 2 on this column and 4 here, because we've just doubled up the place values all round. And now we have just one signal left of place value 2. So that would be the 2's of the answer. Finally, in place value 4, we have 2 signals, and we have one full adder left. A full adder wants 3 signals, so we can just feed it an extra constant 0. And now we're adding up 3 things. The outputs will have place values 4 and 8. And that leaves us with these as the only signals with those place values. So they must be the answer signals. And there we are, we've built our circuit.